Welcome everyone to this fortnightly CQC2T online seminar series. Today we have two talks from the ANU node, one talk in theory and one talk in experiment. The format is going to be about 20 minutes to 25 minutes talk, and then 5 to 10 minutes of questioning per talk. First we have Ruvi, who's going to talk about his theory project on how your choice of measurement basis bounds estimator error. And over to you, Ruvi.
Yes, can everyone hear me?
Loud and clear.
And see my screen. Good. Okay, so the title, I'm sorry, that's a bit of a mouthful. I came up with that in a bit of a hurry. So a bit more briefly. Hi everyone, I'm Ruvi. I'm a PhD student in Pinkoy Lam's group at the ANU, supervised by Pinkoy and Joe. And this is some work that was done in collaboration between the ANU and with some Singapore. So the title's a bit of a mouthful, but in short, what we did was we came up with some new inequalities in information theory. But what do these inequalities do? Let's suppose you want to measure a magnetic field. How do you do this? Well, you take a qubit in some sort of probe state and you interact it with the field. Now, based on the state of the magnetic field, the qubit will now lie, it'll be rotated to lie in the XY plane. So what I'm trying to show with this circle is that it'll be in some sort of a pure state. And if we don't know anything about the magnetic field, it'll be uniformly distributed somewhere in the XY plane. But often, it won't be uniformly distributed because we will have some sort of prior knowledge. And based on our prior information, we might have this kind of Gaussian distribution, where the qubit might be most likely in the Y direction and less likely out here. So I just want to stress that the qubit will be in some sort of a pure state, but based on our prior information of what the magnetic field is, we know that it's most likely here and less likely around here, meanwhile almost definitely not here. Now the question is, how can we use this prior information to make best measurement? And even when the prior is very complicated, because you can imagine you send a qubit to interact with the field, you measure it. Using the result of this measurement, you update your prior, send a new qubit, measure it, update it, send another one, measure, update it. After you do this 5 or 10 times, you might end up with a very complicated looking prior. With the previous one, it might have been kind of obvious in what direction to measure. But when you've got a state like this, it will be less clear. So that's what our inequalities do. So as an overview of the talk, we're going to talk about 1, the error of an estimator. 2, we're going to introduce the tools from information theory that we use to solve this problem. Then we're going to introduce some tools from circular statistics. And lastly, as an example, we're going to talk about qubit measurement. So the things that we introduce kind of work, they're general inequalities, but for this talk, we're just going to specialize to the example of measurement on a qubit. So the error of an estimator. So we want to estimate some sort of quantity, phi, and we make a bunch of measurements, Z1 to Zn. So for Z1, again, we send a qubit to interact with some sort of field, and then we measure it, for example, in the sigma x basis. So Z1 might be spin up or it might be spin down. Then we send a second qubit, and maybe we measure that in the sigma y basis. So Z2, again, will be spin up or spin down, but in a different basis, and so on. Then we feed these results up, down, up, down to some sort of classical algorithm. That's what phi hat represents. And then that's like a classical algorithm processes these and spits out some sort of estimate of phi. And the error will be given by phi hat minus phi, the deviation. But this error depends on 2 things. 1, the measurement results, right? Because we might be lucky. We might get a bunch of measurement results that help us immediately hone in on the actual value. Or we might be unlucky. We might get a bunch of very unlikely measurement results just by chance that completely mislead us. Or 2, it depends on the parameter value. Like let's say we're estimating the separation between 2 point sources with some sort of width. If they're well separated, it'll be really easy to estimate their separation. Meanwhile, if they're starting to overlap, it'll be hard to estimate their separation. Now, you might have heard of Fisher information methods. Now, Fisher information methods average over all possible measurements results, but they do this for a given value of phi. So that's what I'm trying to show with this notation here. You're averaging over your measurement results, but not your value of phi. So Fisher information actually kind of assumes that you've narrowed your parameter down to like a very narrow region, and you're trying to make your estimate even more precise. So Fisher information is very useful in a lot of cases, but because of this sort of assumption, it just can't handle a prior distribution. It assumes you've got a narrow range of phi and you're trying to get even better. What we want to do are Bayesian methods where you want to average over both phi and z. And if you want to do this, you're going to have to use a bunch of tools from information theory. So the basic item of information theory is what's called a random variable. So that's a thing that has n possible outcomes with probabilities p1 through to pn. So an example could be a coin flip. It has 2 possible outcomes with 2 possible probabilities. Or maybe a qubit measurement. It has 2 possible outcomes, up or down, with, again, 2 probabilities. Now, the entropy is something that measures how random your random variable is. Now, for one thing, it's just a number. You say, how random is this qubit? And it'll spit out something like maybe 5. And you can say, oh, that's more random than 4, but less random than 6. But a way of thinking, actually seeing what entropy means, is let's look at the example of a biased coin with probability p. So our coin will be heads with probability p, or tails with probability 1 minus p. But just before we move on, I want to say why entropy is so useful. So the fact that entropy is summing over our entire probability distribution is why we want to use entropy. So Fisher information is based entirely on derivatives. And derivatives are like local quantities, right? The derivative of a function lives at a point. And so it can't see what's going on elsewhere. And so it just works locally. Meanwhile, entropy is the opposite of a derivative. It's a sum. You sum over the whole distribution. And that's why entropy is like the natural thing to work with when you want to incorporate a prior. You sum over the whole distribution rather than differentiating it at a point. So we have a biased coin with probability p. So what I've done here is I've plotted 2 to the power the entropy as a function of p. So the x-axis is the probability that my biased coin will give me heads when I flip it. So our state space has a volume of 2. Our coin has 2 outcomes. It can either come heads or tails. So first, and depending on the value of p, x will occupy some subset of the state space. Firstly, suppose that p is equal to 1. So our coin is always heads. So x occupies a volume of 1, right? Every time you flip it, it'll always occupy just half of our state space, a volume of 1. And 2 to the power h of p is 1. Meanwhile, what if p is equal to a half? Now our coin is heads half the time and tails half the time. It occupies the full volume of our state space of 2. And 2 to the power h of p is 2. So the way I like to think of entropy is that our random variable has some sort of state space, but depending on the probability distribution, it will actually occupy some kind of subset of our state space. And if you look at 2 to the power of the entropy, you get the volume of the state space that your random variable actually occupies. And this is actually a general rule of information theory. If you kind of want to understand some abstract quantity in information theory, just take 2 to the power of that quantity and you'll get some sort of a volume. This works in both discrete and continuous information theory. So let's come back to estimation and entropy. So we want to estimate some sort of parameter phi. We pick a basis and we make measurements z. And based on z, our knowledge of phi increases. But again, what do I mean by knowledge increases? What do I mean for my knowledge to increase? Knowledge is quantified in information theory by a quantity called the mutual information. How do we understand mutual information? Well, you just look at 2 to the power I. So we can imagine initially phi is occupying this whole volume here. But if we look at our measurement results, we can imagine that this volume that phi is occupying will shrink by some amount. And by what amount? We'll look at 2 to the power I. If 2 to the power I is 2, that means after looking at our measurement results, we can halve the possible value that phi will occupy. Meanwhile, if the mutual information is infinity, that means we learn everything about phi. It contracts to a point, and we get the exact value of phi after a single measurement. So what we want to know is how big can the mutual information possibly be? And the answer, which is the first result of our work, is something called the CIX equality. So on the right, is something called the Holevo information. So the Holevo information is something that's been around a long time. So it's something that's easy to compute, and it comes from, you just look at our measurement scheme, and what it is you look at your measurement scheme, and what it tells you is, if we didn't just interact one qubit with the magnetic field, but if we took an infinite amount of qubits, interacted them all with the magnetic field, passed them all through some kind of giant entangling measurement, and performed the best possible quantum measurement on all of these infinite qubits, how much information would we get per qubit? So chi would be like, if we were the most possibly advanced alien race, how much information would we get per qubit? It's like the best we could possibly do, but it's really easy to compute. Now I, as we've said, is the amount of information that we get in reality. It's the thing we care about. Meanwhile, this CE quantity, this is something called the coherence of encoding. It's something that you can easily compute. We've put its definition here. And if you know a bit of information theory, you'll notice that it looks a bit similar to the definition of the Holevo information. What it tells you is how much information loss is caused by projective measurement. It quantifies this penalty. How much information are you losing? How much less effective is a projective measurement on a single qubit than the Holevo information? And it's based on this thing here, which is the quantum relative entropy. Now, the quantum relative entropy is a generalization of something called the classical relative entropy. So the classical relative entropy asks, if I substitute one probability distribution for another, how much information do I lose? And that makes sense, because what we're asking here is, if I substitute rho for the same state but decohered in the measurement basis, how much information do I lose? So it makes sense that this is the quantity that shows up when we're asking, how much information do we lose when we make a measurement in the Z basis? So this sort of quantity has shown up in various guises. In information theory, it's known as coherence, but it's also showed up in a paper by Hall and Wiseman in 2012, where it was called the G asymmetry. And so what we've got here is an easily computable measure of the information loss caused by projective measurements in some basis. And we can use this equality to convert some general bounds to basis-dependent bounds and use these to come up with adaptive measurement schemes, which we'll talk about later. But here's an application of the CIX equality. So let's suppose that our state, the magnetic field, is encoded in our state via a unitary rotation. So up till now, we haven't actually assumed how the magnetic field is encoded in the qubit. It could have been encoded in any way, even a way that completely breaks the laws of physics, and our equality will still hold. But here we'll just assume that phi is encoded via a unitary rotation. So this is a result here. I'll just go quickly through this, but you substitute in the definition of the mutual information, and you get a bound here. So on the left, you have your prior information about phi. Here, mutual information, the information about your estimator. And on the right, it's the deviation between your estimator and the parameter. It's the entropy of that deviation. And the thing is, you don't really care about the entropy of that deviation. You want the error, right? But what Hall and Wiseman do is they use this cool fact. A Gaussian has maximum entropy for a given variance. And variance and error are kind of the same thing. That lets you jump between entropy and variance and error. So they turn the right-hand side into an error, and you get a lower bound on the error. And we can substitute the CIX bound into that. We can do some algebra. And the main result is now we have a lower bound on the error that depends on your measurement basis. So if we come back to this idea of the qubit, what that means is we can say, if we measure it in this basis, what's our error going to be? And as we rotate our measurement basis, we can get a bunch of different errors. And we can pick the basis that'll give you the lowest error. And then every time you measure the qubit, you get a new prior, you get a new bound, and you could imagine designing some kind of optimal measurement scheme that keeps measuring in the basis with the lowest error. But before we do that, we're going to have to take a slight detour and talk about circular statistics. So let's say we measure n qubits and we get n separate phases, phi 1 through to phi n. Now, back when I was in first year labs, which as a theorist is about as far as I got with labs, I would have been like, what's the actual phase? Well, that would have been like the average phase. So I would have just gone and been like phi 1 plus phi n divided by n. Then I would have been like, well, I need some kind of an error with that. So I would have gone and calculated the variance. Is that correct? Is that right? And the answer turns out to be no, because unfortunately, a lot of our usual stuff actually breaks on the circle. So to see why that is, suppose a system has a phase of 0, but we measure 2 pi minus epsilon. Now the error of our estimate should be epsilon, right? But if we naively compute the difference, we'll find that the error is equal to 2 pi. The problem is our usual statistical measures like mean and variance, they're not adapted to the topology of the circle. So another way to see that is, let's look at this distribution here, which is like a circular sort of Gaussian. Now it's centered on 0 and it has a variance of 1.6. Now let's just shift it to the right a bit. Now, if mean and variance are working correctly, the mean, the dashed line, should lie here and the variance should stay unchanged. But actually the mean now lies over here and the variance is something completely different. Problem is mean and variance are making these same mistakes as are up here. They're just not adapted. They don't understand that 0 and 2 pi are the same thing. So how do we deal with? We have to work with the circular mean and the circular variance. So let's say you give me 3 angles and ask me to compute the average of these 3 angles. What I have to do is I have to put these 3 angles on the circle and average them on the circle. So this R is what we call the resultant vector. And what we do is this actual angle here is what we call phi bar. This is the circular mean. And you can find an exposition of this in topics in circular statistics down there. And what about the circular variance? So here I have the same thing for a lot more dispersed angles. And you'll notice that if the angles are more dispersed, this resultant vector has a shorter length. And this is a general result. The more dispersed the vectors are, the shorter the resultant length is. And so in classical circular statistics, which is a field, it was invented by, I think, geologists and biologists. You know, you look up to the sky, you see a bunch of birds, you're like, what's the average direction those birds are flying in? So the circular mean, you take the average of the points on the circle, and the circular variance is defined as normally 1 minus r. We've added a factor of 2, and you'll see why that is. And if you look at this and you're thinking Holevo variance, if you ask us about that at the end of the presentation, there's some interesting discussion around that. But now, armed with this, before we said that this was the error, but now we're saying that we should use a circular definition of the error. And in the paper, we show that this is what you should use. So this is the regular error, and this is the circular error. They agree for small errors. That's why we need that factor of 2. And at large errors, they become periodic. And one is we can show that this is a natural definition of error on the circle. So the square error has a lot of properties. For example, you can show that this error is equal to the bias plus the variance of your estimator. And we prove that this is equal to the circular variance plus the circular bias. So it's not just nice, it has the same natural properties that this estimator has. And it's equal, sorry, that this error has. And it's equal to this error for small deviations. Secondly, it has nice entropic properties. So if you remember, there was this step from before where you have this entropy that you don't like, and you jump from entropy to error by saying a Gaussian has maximum entropy for a given variance, and variance is the same thing as error. But the problem is, now that we're on the circle, variance isn't the same thing as error. Circular variance is the same thing as error. So what we want to know is there a distribution on the circle that has maximum entropy for a given circular error? Because if we had that, then we could do an analogous thing to this step of the proof. And the answer is there is. It's something called the von Mises distribution, which if you just eyeball it, it looks exactly the same thing as a Gaussian on the circle. And it's what I've been showing you all this time and calling a Gaussian on the circle. But using that, we can derive a new bound. This is called this is the entropy of the von Mises distribution inverted. It's easy to compute on a computer. And we now have a bound on the circular error. And substitute the CIX equality into this, and you get a measurement dependent bound. And lastly, I'll take you through how you can apply that to qubit measurement. So let's say we come back to that example. You interact a qubit with a magnetic field. That magnetic field has some kind of prior distribution. So now we want to measure this qubit. So this is what a von Mises distribution looks like. It looks like a Gaussian on the circle. Now let's say we measure our qubit along the x-axis, and let's say we get spin up. So just to clarify, by the way, how I've defined my phi is defined as the angle with the x-axis. Now, if I get a spin up, that tells me I'm more likely to be in this quadrant and less likely to be in that quadrant. So what that does is it'll pull my distribution to the left. And let's say I measure it, I send another qubit to interact with the field. I measure it again and I get spin up again. It'll pull it to the left again. And if same thing happens, it'll pull it to the left. Now let's say I feel like some variation. I send a qubit to interact with the field, and this time I measure it along the y-axis and I get spin down. Now I'll start to get some kind of weird thing happening with the probability distribution. Because I got spin down, I know I can't have any probability of being around here. That's why I get a node here, and my distribution gets a bit of a bump. So up till now, the way the distribution shifts in response to these measurements is fixed by the laws of probability and Bayes' theorem. Like, there's no choice here. But given this probability distribution, I now feed this distribution to a bunch of different algorithms to try and guess what the value of phi is. So one way of doing it is, how do I use this distribution to guess what phi is? One way would be take the average of this distribution to see what phi is. And that corresponds to the mean. The other way would be to just pick this top value up here, and that corresponds to the mode. And also there's one that corresponds to the median, which is pick the point that has equal area on each sides, but I won't do that here. But either way, you have a bunch of different algorithms you can pick, and R bounds give you a bound on the best possible choice. But typically this one here actually ends up being optimum, so this is the one we'd normally go with in practice. But measuring in X and Y, as you can guess, isn't going to be optimum. And if you looked at this distribution here, can you imagine kind of looking at this and thinking, what angle should I measure in now to get the most information from my next measurement? You know, what angle should I pick? Oops. So earlier we derived this inequality here, which was a lower bound on the circular error. And when we substitute in CIX, we get this lower bound. So we have a bound on the circular error, and we want to make the circular error as small as possible. So these two quantities here, they're quantities that depend on our experimental scheme, not our measurement scheme. They're the same no matter how we measure. This CE is the only thing that depends on how we measure. So if we look at this particular scheme, this particular prior here, what we do is, I just calculate CE of Z for each possible measurement angle and just pick the angle that has the lowest error and measure with that basis. And you just keep repeating this, and each individual measurement will be kind of the individual optimum measurement. And that kind of gives you a little optimum scheme. And so here's a little example of that. If we look at this particular distribution, and this is a plot of CE of Z as a function of phi, it's lowest when phi is equal to 0, which is telling you to measure along the x-axis. And that kind of makes sense because an x measurement is the one that gives you the most information. If you measured along y, you already know what's going to happen before you measure. It's going to be spin up. It's almost not likely to be spin down at all. Whereas x is going to give you the most information. Another cool thing when you look at this plot is, if you remember from before, we had c plus I is equal to chi. The fact that C is never 0 ever tells you that your mutual information is never equal to the Holevo information. So no matter how you do a projective measurement on this system, there is always going to be a quantum advantage. It is always going to be better to send in, say, 3 qubits and take them out and do an entangling measurement than just send in the qubits one at a time and projectively measure. So it's like a nice kind of really quick way of just cutely proving that there's a quantum advantage in this scenario. And this is just the result of doing 5 measurements using the adaptive scheme. And you can see that more measurements are better, which is what you would expect. So in conclusion, if you want to incorporate prior information, then entropy is your friend, because entropy sums over the whole distribution. CIX equality is a nice way of showing you how much information you lose due to a choice of projective measurement basis. Phase estimation calls for circular errors, and we can find a lower bound on this using entropy. And as a cute application of all this, put the two together and you get adaptive measurement algorithms. So thanks for listening. Here's everyone who was involved in this. We don't have the paper on the archive yet, but if you're interested in this, please send me an email. I'd be happy to discuss this with you. And if you have any thoughts about this or anything at all, I'd be happy to hear questions or happy to discuss this over email. Thank you for listening.
Thank you, Ruvi. So we are now open for questions. You can either ask directly or put it on the chat and I'll repeat your question to everyone.
Yeah, hey Ruvi, it's Jeff here. How you going? So since you prompted me, can I ask you about the Halevo variance?
Yes. Okay. So this is one of those things where, so let's see. So if I go back to there, where was the circular information that is here? That came up here. So in doing this, we actually, so the timeline of this was actually, so we first calculated the bound, and then I wanted to do a bunch of examples of qubit measurements, and all the results were rubbish. And then I realized that, of course, I need to learn some circular statistics. And so in classical circular statistics, everyone looks at these sorts of quantities. And I didn't actually know the Halevo variance existed, and that's why I initially studied this quantity. And then it was only later that I kind of found out about the Halevo variance. So for people who don't know, the Halevo variance is defined this way. And this looks strange, but the reason, one kind of advantage of this is this thing gives you uncertainty relations because it can be infinite when R is equal to 0. And we have number phase uncertainty relations. But one is, I'm pretty sure that minimizing the circular variance will also minimize the Halevo variance. Like I think, like studying one will study the other. And as we've seen, studying this, like this has a lot of natural properties, and also it has a lot of natural entropic properties. Like the von Mises distribution is like the circular Gaussian. It's like the natural circular analog of the Gaussian. And the von Mises distribution, its natural variance is to look at this. So I think I don't quite fully understand the relation between the two. And if you have opinions, I'm very interested in hearing them. And so I think in conclusion to that, I need to learn more about this and I'm keen to hear more. But I think I'd say studying this and studying that are probably equivalent is my guess. Does that answer the question?
Yeah, no, thanks. I was just curious. I mean, I guess I've always just used the Halevo variance and have never really looked at the circular variance. So we're the opposite in that sense. So maybe we can learn something together.
Yeah, I'd be really keen to see a difference.
Thanks.
Yeah.
Any other comments or questions from others?
Yes, Michael Hall here. Ruvi.
Michael. Hey, Michael.
How are you? The optimal bound that you talk about, I assume it's just asymptotically optimal. You don't actually saturate the bound. Is that right?
Which bound, sorry?
Well, you talked about being able to, what was it, make C equal to 0 or choose your experiment optimally. In what sense is that optimally? Is that in the sense of being then able to saturate the bound or not?
Oh, yes. So that would be, if I bring up, so that's the bound that was a generalization of the bound that you had with your PRX with Wiseman in 2012, right? Mm. So that's this one there, if I bring it up. So if I remember right, and I've also got that paper open in another screen, I've got my notes on it. So this bound, if I remember, for it to be saturated, you needed your estimator to be unbiased and the errors to be Gaussian distributed and independent of the value of the estimator. And I think in the circular case, you need the errors to be von Mises distributed and independent of the value of the estimator. Does that answer the question? And so in this case, the errors will be coming from your like quantum measurement errors, like when you measure it and the...
Okay, yeah. So there's still a minimum error, are you saying?
Yes.
Yes. Okay, good. That's fine. Thank you.
We have time for one more question.
Hello, Henry here.
Hi, Henry.
Yeah, hi. So very good talk. So you have been talking about about the circular estimation. So I was wondering, because we measure spins in like all axes usually, is there anything more like a spherical estimation for the spin instead of circular?
Honestly, I don't know too much about that. So spherical estimation. So what do you mean by that? Sorry. So what does the space look like?
So for example, we want to measure our spin in all the three bases, X, Y, and Z. So where it can be random.
Yeah.
Yeah.
So I think it would be interesting to see how this generalizes to when you have multiple parameters. And I think that is the natural way to see how this generalizes. But I don't have anything to say about that at the moment. But that is a very interesting question.
All right, thank you.
Yeah, thanks.
Okay, thank you everyone. And thanks Ruvi for the great talk. We now move to the second part of the seminar. The second part is going to be given by Hao. Hao's title is Teleporting Coherent States of Photons with Reduced Decoherence. Over to you, Hao.
Thanks, Pinkai. Just share my screen. Can everyone see the slides? Can everyone hear me clearly? No muffled sound, I think. Okay, great.
Very clear in Melbourne.
Oh, thank you very much. Good afternoon, everyone. My name is Hao. I work in experimental quantum optics, supervised by Pinkai. So it would be quite a different taste to what to the talk that Ruvi gave. Ruvi was very humble when he said that he would average n values of phase measurements by summing them up and dividing by n, because he that's what you did in the undergraduate labs. What he didn't know is that that's still what we do even outside of those labs. Anyway, so my subject today is on quantum teleportation. So quantum teleportation, as many of those in the audience would know, is a very important device in quantum communication and computation. So in teleportation, what we do is we prepare a source of entangled states. We take one part of this entangled state, interact it with an input state, perform so-called joint measurements on these two systems, and the outcomes we feed forward to the other half of the entangled state. And by some simple unitary transformations, we can reconstruct the input state at the other side. This is very useful in communication and computation because it gives us a simple way of distributing quantum states, often across long distances. Therefore, quantum teleportation is usually an essential ingredient in most quantum repeater proposals and their small scale realizations. In quantum computation, quantum teleportation is slightly more niched. However, it is regularly used because certain models of quantum computation make use of of it. I'm referring to measurement-based, one-way quantum computers, aka cluster state computing, where you provide a suitable entangled source to the teleporter, and depending on what entangled source you provide to it, the teleporter not only transmits the states but also adds a processing step on top of it. Now, it can be argued that we know almost everything there is to know about quantum teleportation. For example, we know that all teleporters fall under two categories: discrete variable, continuous variable is the name I will refer it to. It's categorized based on based on the dimension of the entangled state you provide to it. If you provide to it Bell states, then you can teleport quantum states such as qubits. If you provided to it an Einstein-Podolsky-Rosen entangled state, then you can teleport states of arbitrary superpositions in the Fock states. It is also true that discrete variable teleportation is easier to implement, 0, 1, 0, 1s all the time, whereas continuous variable is a lot more difficult. We also know as a fact that in discrete variable teleportation, particularly with photons, it always comes with a 50% probability of success, because certain outcomes of the joint measurements cannot. Is there something going on in the chat, sir? Cannot be. Okay.
Don't worry about the chat.
Yeah, I thought maybe the sound or something. Okay. So I was talking about the 50% probability. So we know as a fact that the discrete variable teleportation using photons only succeeds with 50% probability, because some of the outcomes of the joint measurements cannot be distinguished, and they must be discarded. So we know a lot of facts. In spite of this, there are unsolved problems regarding quantum teleportation. So in continuous variable quantum teleporter, the fidelity of the teleporter depends very much on the EPR state that we supply to it. The EPR state, the required EPR state, is unphysical, and any implementation of CV teleportation is necessarily an approximation. So the question is, how far can we push it? The group of Furusawa at the University of Tokyo has made a number of good experiments in investigating this problem. And what they showed in 2008 was that optimized with about 8 or 9 dB of squeezing, and optimized by keeping the optical loss as low as they can, what they got was about 83% of fidelity, significantly lower than what one might get for many other systems. So the question is, how far can we increase it? If, according to Brownshire and Kimball, in order to increase the fidelity in CV teleportation, we must push the squeezing as close to infinity, but that is impossible. The first recorded squeezing was in 1985, and 40 years, 35 years, 40 years now, we've only got 15 dB of squeezing. The more squeezing we have, the harder it is to use it. And so increasing squeezing in order to increase the fidelity of CV teleporter is a difficult route. Now, it has been proposed by some authors that there are other methods for increasing the fidelity and reducing the decoherence in CV teleportation. It has been proposed that you could distill the entanglement. So you generate the entanglement first, and then you combine multiple copies into one good one, and then you teleport with this entangled resource. And that should give you, in principle, that should give you a high fidelity. Or you could implement quantum error correction on the input state to protect the state against the decoherence introduced by the teleporter. But so far, none of these experiments, none of these proposals, which are all extremely challenging to implement, has actually been demonstrated. In Canberra, we are looking at a line of attack using so-called noiseless linear amplification. The noiseless linear amplifier is a strange operation. It's not unitary, it's not bounded, it's not physical. It's represented by the operator g to the power of n hat, where n hat is the photon number operator. This operator itself it's not particularly meaningful until you act it on the coherent state and you see that it amplifies a coherent state without adding any noise. Hence the name noiseless linear amplification. Or you could also act it on EPR states, and that will increase the entanglement of the EPR state. Or you could, as shown by Austin and Tim, that you could also act the noiseless linear amplifier on an entangled state with loss, and that would simultaneously increase the entanglement as well as reducing the loss. So it's a very powerful device for reducing the decoherence in continuous variable quantum systems. There are several physical implementations of noiseless linear amplification based on quantum scissors. These are very difficult experiments. They're somewhat related to the hybrid program going on, where you're using single photon technology. You're combining single photon technology with continuous variables, and they're very challenging. They have demonstrated, I believe Professor Jeff Pryde's group have demonstrated amplification of coherent state, distillation of entanglement. It has been very difficult to scale these challenging experiments up to, for example, a scale like teleportation. In Canberra, we have been following a complementary approach, which we call measurement-based noiseless linear amplification. And what we make use of is a fact noted by first by Fura, second Cerf, that noiseless linear amplification can be implemented in the measurement-based manner. What I mean by this is if you have a state rho, you act noiseless linear amplification on it, followed by measurement, that is equivalent to post-selecting on the measurement outcomes of that state without the NLA. So with this device, it is possible to perform several operations that you'd be able to do with a noiseless linear amplifier without actually having the physical noiseless, the physical implementation of the noiseless linear amplifier. Over the past few years, we've done several experiments on this. For example, quantum cloning, and we did one on squeezing gate as well, putting a measurement-based NLA into a squeezing gate to increase the fidelity of that gate. We also use this to investigate the properties of several entanglement measures. And so what you can see is that the MBNLA shares much the same properties as the NLA. I would like to discuss one of these experiments in slightly more detail. So in this experiment, an EPR state was prepared and sent through some loss. And usually where there would be a noiseless linear amplification, a noiseless linear amplifier, we detect and post-select according to the filter specified in the equation in this slide. What was found was that the entanglement increased in exactly the same way as what we expect of a noiseless linear amplifier. Now, the problem, there are several problems with this. One problem is that the MBNLA always has to be preceded by a measurement. And in optics, that's a problem because if you measure, you destroy your state. That's why using the MBNLA, it is not possible to create a freely propagating entangled state that has been distilled. Nonetheless, it does show all the characteristics of noiseless linear amplification. So it was this idea that led us to consider putting the MBNLA inside the teleporter because what we thought was inside the teleporter there's the joint measurement, and the joint measurement required for a teleporter is exactly the same as that needed by the MBNLA. So in other words, the teleporter is ideally suited for implementing measurement-based noiseless linear amplification. Here is a schematic of the experiment that we did to test these ideas. We set up a simple teleportation apparatus that physically is the same as other teleportation, but the difference is that after the joint measurements, we implement a post-selection step where we decide whether a specific outcome is accepted or discarded based on the measurement-based noiseless linear amplification. So what we observe is that as we increase the gain of the MBNLA, the teleportation fidelity increases. The maximum fidelity we got was 92%, as opposed to the 83% that you would have without MBNLA. It is perhaps implicit in this figure how the MBNLA fits into the teleportation protocol, but I also have a simulation here showing how this thing works. The idea is that normally the output state of normally when you perform no ordinary teleportation, the output state is decoherent. However, by adjusting the gain of the feed forward of the teleporter, it is possible to reduce the decoherence introduced by the teleporter at the cost of also reducing the signal strength. Now, if we were to simply turn the feed forward gain back up, we would get all the decoherence back. However, if we perform noiseless linear amplification, then we could amplify this state without adding any noise, and we could recover the signal strength without also getting back the excess noise. And it is because of this that it is possible to get an improvement in the fidelity and to reduce the decoherence of CV teleportation using measurement-based noiseless linear amplification. There are several assumptions and that must be justified and limitations that must be discussed about this experiment. The first thing is that in most noiseless linear amplification experiments, there's always non-Gaussian effects. What we found in our case is that the non-Gaussian effects are usually negligible, that the output state was always very close to a coherent state, and the mode of failure of the teleporter is that we get compression effects. So if the coherent state we put into the teleporter is too big, instead of getting a very non-Gaussian output distorted by noise in the amplifier, what we get is a state that's much smaller than what we expect the output to be. But provided we operate within the dynamical range of the amplifier, then there is no such effects, and there are no non-Gaussian effects. The range is about, I think, alpha with alpha equals to about 0.4 for the experts. That's the kind of state we can put the MBNLA can accept. The probability of success is of our experiment is typically 10 to the -5 to 10 to the -6. It depends on how big the gain we put in. The higher the gain, the higher the gain we use, the lower the probability of success. But at the best fidelities, this is the kind of values we get. So it must be stressed that this teleportation protocol with reduced decoherence cannot be deployed immediately into some sort of QKD or repeater setup in spite of the increase in fidelity. I think that is a very important problem, and we are working with colleagues from Queensland, Tim and Spiros, who until recently was with us in Canberra, of an alternative arrangement where we might be able to still get this reduced decoherence, but that it would work for QKD and other applications. It is an interesting problem, but it requires further consideration. So in conclusion, I would simply like to state that we have shown, our experiment shows that coherent states can in fact be teleported with reduced decoherence. And the surprising fact is that this can be done without recourse to the normal techniques such as entanglement distillation or quantum error correction. So this also happens to be my final PhD talk. So I would like to take a moment to thank everyone who has helped. Thank the group who has helped me a lot during my PhD. I must mention Zhao Jie, who has since graduated and is I believe is now working at NIST. She built much of the teleportation setup and obtaining preliminary results. And also Liu Kui, who helped us with squeezing gated teleportation. I'd like to thank my other lab partners and the members of the team. I would also like to thank Assad and Pinkoy for supervision, and also acknowledge our collaboration with Tim and Spiros, who have been providing us with very fruitful lines of research. And that's all I have. Thank you.
Thank you, Hao. We're now open for questions or comments. Would anyone like to ask or give any comments?
I might ask a question. Very nice talk, Hao. You mentioned a few times you could use this to teleport coherent states, but is that just because that's what you did in the experiment? I mean, would this work for other states to decrease the decoherence as well?
So first of all, yes, in our experiment we use coherent states and only coherent states. Regarding generalization of this protocol to other states, the obvious choice, I believe, would be cat states. Perhaps that's the example you're thinking of. I think it is easy to think, it is easy to probably easy to see that it will not work, at least the exact same protocol, because no matter which outcome occurs, at the joint measurement that we get at the joint measurement, it will always herald a decoherent cat state. And if we combine an ensemble of these decoherent cat states, then no matter how we post-select, we can never recover a perfect cat state, unlike the case of coherent states where it is possible to recover the coherent state. But if we really wanted to use a cat state, then the only possibility is to shift the MBNLA from the measurement, the joint measurements and the teleporter into the other side, so on the receiving side. I believe you have mentioned this idea previously, and also Spiros has been talking about it.
But I realize it's much harder to teleport something like a cat state. I was thinking more of like just squeeze states, perhaps. But does it really matter? I mean, a CV teleporter can, in principle, teleport any state. Is there? I'm not sure I understand that there's anything specific to what state you're teleporting going on in your post-selection. I mean, I understand that experimentally this might be hard, but if someone gave you a supply of cat states to teleport, or various squeeze states, wouldn't the teleporter still teleport them better with MBNLA?
If we have squeeze states, in particular displaced squeeze states, that's very important to have a displacement on it. In the same way you have a displacement on coherent state, then indeed the fidelity would go up. Whether it's useful for anything, well, I'm not too sure about it. The fidelity would go up, but the squeezing would not. So the amount of squeezing you have at the output will always be limited by the squeezing you get after each conditional measurement. If you herald a specific state, you get a specific amount of squeezing, that is always the maximum squeezing you will get, and that squeezing is always less than the amount of squeezing you put in. So the fidelity will not go to 1, but yes, if you do put the stick, if you do put displacement on it, then yes, the measurement-based NLA will amplify that displacement and increase the fidelity.
Okay, thanks, Will. We should talk about this again sometime.
Okay.
If I could add maybe one point
Joe?
that maybe Tim was, I think Tim mentioned is maybe it was confusing, that a CV teleporter in principle should teleport everything. With the MBNLA, that is not the case. And so the only claim we can make for this experiment is that it is able to teleport the coherent state with reduced decoherence, not only because those are the states we teleport in the actual experiment, but also because it's something to do fundamental to do with the scheme.
Is there still time, or should I do it another time? This is a somewhat distant, naive question. It's about the gap between, I guess, the motivation and the practical engineering applications of something like this. If you've got an imaginary process that would absolutely be amazing in some kind of quantum information protocol because it breaks no cloning or something, like the noiseless linear amplifier, you think, all right, so that can't work. I only wish I had one. But then you find a probabilistic algorithm, a heralded probabilistic method of making it. What is known about the usefulness of such a device in terms of, I would imagine there's quite possibly some fairly strong things you could say about under what conditions it doesn't, in effect, get your scaling back for a quantum device, or under what conditions it does.
I just want to check I understand your question, right? Are you asking what a noiseless linear amplifier, what you could do with a noiseless linear amplifier?
What you could do with a heralded probabilistic one, as opposed to the unphysical idealized version. I mean, when you start off thinking about these things, you think, if I could have a box that did X, then I would solve a whole pile of problems. And then you realize that's unphysical, but I can get this compromised version. I guess I'm asking what is known about the nature of the heralded probabilistic nature of it and scaling. Or is that just like a big scope question for another time? I don't know.
If I could interject, I think the heralding is an important point. If it were just a protocol that's completely randomly probabilistic, then it's of no use at all. But the heralding means, especially for the quantum cloning case, we do have a light that lit up and go, bing, you have created five clones in our experiment. But we still need more examples. Now, what do you do with the 5 clones? You know.
I mean, you also, to be really engineeringly useful, you have to be able to do them in parallel. So you say this
Yes.
999,000 didn't work, but this one did. We'll use this one.
Which means that you have to store it in a quantum memory and try and line them up so that they are consecutively occurring.
Yeah. Okay.
If the question is about what the probability of success of the NLA, what penalty this would introduce, then yes, you would need a quantum. For example, if you're transmitting quantum states, then you would need multiple quantum memories to store the state and to reduce the overhead. But to be honest, I'm not entirely sure I understand the question.
Okay, thank you.
Okay, so thanks, Hao, and thank you, Ruvi, as well, for 2 very interesting talks. I'd just like to advertise that the next CQC2T seminar is going to be on the 13th of October at 2 p.m. and it will be hosted by the UNSW in Sydney. So thanks again, everyone, for your attendance. I'll see you in a fortnight.